Question 3.1. Describe the pattern produced on the screen. This would be a pattern produced on the screen. You would have a central maximum fringe, and you've got fringe separation due to constructive interference. Here are the fringe. These are constructive interference, and these ones are destructive. So we call that one maximum. Maximums all are maxima, and they are purely green because we're using green filter, and each fringe separation, which is W, that's a fringe separation W, and each separation is similar, they're the same, but the intensity, the further away from the central maxima, will decrease as you go down to the left and to the right. From the center of the central maxima, it's symmetrical. Question 3.2. The green filter is replaced with a red filter. Well, the wavelength of the red is bigger than the wavelength of green, so fringe spacing will be wider. As you can see from the equation here of Young's slit equation, the fringe spacing is equal to lambda d over s. You can see that lambda increases, then W will increase, and W is fringe spacing. Therefore, fringe spacing is directly proportional to lambda. The central maximum will be wider too, because of we're using larger wavelength. Question 3.3. We need to calculate the angle theta between the first order maximum and the central maximum. You can see the diagram that this is the central maximum, and that's the first order. So this is zero order, and that's the first order, where here n equals 1. And that's the angle theta we're looking for. And so we're going to apply the equation for applying diffraction grating equation, which means we need to know what n is. So n is 1. We know lambda has been given to us, 650 nanometers. And we know what d is because we've got 500 lines for every 1,000th meter. That means 1 over 1,000 meter. So each line is d, which is slit spacing. So all we need to do is say, well, we've got 500 d that fit into 1,000th. So if we divide 500d by 500, we get 1d. So we have to divide that by 500 to get the distance of 1d. Therefore, d is 1 over 500 times 10 to the power 3, which is d, then gives 2 times 10 to the power minus 6 meter. So that's our d, the slit spacing. And therefore, applying the diffraction grating equation, we can rearrange to find sine theta, and then find theta, and then substitute the values we've got. N is 1, and we put lambda in there, and we put the value of d, and we found theta to be 18.97 degrees, roughly 19 degrees. Question 3.4. Question 3.4. In practice, the filter transmits red light with wavelength in the range of 600 nanometers to 700 nanometers. So just how this affects the appearance of the maxima. So because we're talking about the appearance of the maxima, we are actually talking about the order, because as the maxima appears, it depends on which order. So the order will be wider because we're going from 600 to 700 nanometers. Gets wider as order increases. Whenever we're changing, when order changing in diffraction grating is considered, we should always check the order at 90 degrees. So for 600, using the diffraction grating equation, plugging in theta to be 90 degrees, so sine theta will be 1. Therefore, you're going to get n lambda equals d, so therefore n equals d over lambda. From there, you know your d because we calculated earlier. So that's d, and divided by n divided by lambda. N would be roughly equals 4.2, so this is a fourth order. And if you try the 700 nanometers, you will soon find out that there will be no fourth order, and therefore the fourth order will not be completely visible. So yes, the central maxima will be unchanged, and the broader maxima of angle for each order. Part of the third order maximum suppressed at long lambda, because this is log lambda, for theta greater than 90 degrees. So this one will not be seen because it's far away. As the order gets, as the order increases, that will not be seen for 700, but the 600 will be of the fourth order, but the 700 will not be visible as the longer wavelength past 90 degrees and we can't see it.